Okay, the subject is equilibrium, which is mostly a different way of thinking about ideas that we have already been working with for quite a while. First definition, back in chapter 5, the word equilibrium was used, and back there it simply meant no net force or no acceleration. And according to Newton's second law, those two are really the same thing. Net force causes acceleration, so if there is no net force, there must be no acceleration. But for a complete, better definition of equilibrium, we say no accelerations whatsoever. That is, none of the meters per second kind of accelerations, and no rotational accelerations either. So now equilibrium means that since there are no regular meters per second accelerations, there is no net force on the object, and since there are no angular accelerations, there is no net torque on the object. Remember, net torque is the thing that causes angular or rotational acceleration in exactly the same way that net force is the thing that caused regular meters per second acceleration. So we, when thinking about equilibrium situations and problem solving in equilibrium type situations, we make use of this a lot. We use this also. We can't forget about this, but this becomes very, very important. So just a reminder, how do you calculate a torque? The magnitude of a torque comes from three factors. First is the magnitude of the force, and second is the magnitude of a displacement vector. Remember what that displacement vector means. Here's some rotating object, just a flat object with it's kind of a weird shape, just to make the point that this applies to any rotating thing, not just a simple rotating sphere or rotating disk. But, so it's rotating about some axis, and we'll say that the axis of rotation passes through this point. And so you could call that, among other things, a pivot point. That's the term that the textbook uses. And you need to choose a reference point before you can figure out any torques. And commonly, it's nice to choose a reference point right at the axis of rotation. And what that really means is that, well, you can choose a reference point absolutely anywhere, but then what you're really doing is you're imagining what things would look like if that reference point were an axis of rotation. Sometimes when there really are rotations with a real axis of rotation, then it makes sense to put the reference point right there at the real axis of real rotations. Other times, like in equilibrium situations, something might not be moving at all, not rotating at all, have a rotational velocity of 0. So in that case, you could pick any point as your reference point, and then imagine what would happen if the object were pivoting around that point, if the object were rotating around that axis. So the book uses the term pivot point. I use the term reference point. They are referring to the same thing. When you pick a reference point, imagine what you're really doing is imagining what things would look like if there were an axis of rotation passing through that point. Or in other words, you're imagining what things would look like if the object were pivoting around that point. Anyway, back to this. This is where we left off in our thinking about the equation here. This displacement vector is always a displacement vector that takes you from, starts at the reference point or pivot point and then goes to the point where the force is being applied. In this case, I'm imagining that this force is just some kind of pushing in this direction on this piece of the object. So of course, if you push that way on the object, it'll make the object rotate clockwise. And then the third term, sine of an angle, the angle is always the angle between the displacement direction. In this drawing, this is the displacement direction. It's the angle between the displacement direction and the force direction. So there's the displacement direction, there's the force direction, so that's the angle. Now let's see how this works, how all this equilibrium stuff and torques work in an actual equilibrium situation. It's for a relatively simple one. Let's say there's two kids on a seesaw, and we don't know the let's say the seesaw is 2 meters long, 2.0 meters long, and there's one kid right out here, say sitting there, and we'll say half a meter away from the pivot here. And we'll say that the mass of this kid on the right-hand side is, say, 25 kilograms. And there's another kid here, a smaller, younger little kid. Somewhere on the right, we don't know exactly where, but equilibrium thinking will allow us to figure out where. So here's the little kid somewhere over here. And the mass of that kid on the left is 20 kilograms. And where that kid is, we don't know, so we'll just say that the distance from the pivot to the little kid is an unknown x. X is the unknown thing that we're trying to solve for. And we can do that with equilibrium ideas. Well, basically, there are two parts to equilibrium. First of all, net force is 0. Secondly, net torque is 0. And that means what we want to do just about every time we have an equilibrium situation is first draw a picture that shows where all the forces are acting. And then once we have that picture, figure out what all the torques are. And then we can write an expression for net force, and then we can write an expression for net torque. So let's see how all that works. First, what are the forces? First of all, of course, there's an upward push, a support force right here at the middle. That's a normal force. We can think of that as the top of this pivot here, or this fulcrum, isn't perfectly flat. It's a surface that's more or less horizontal, and so it applies a push in a perpendicular direction like any normal force, and that's what holds up the seesaw and the kids. And then what other forces are there? Well, there's mass. The seesaw has mass. So there's a weight force on the seesaw. But here's one little trick. Every little bit of that seesaw has some mass. So every little bit of that seesaw is feeling a weight force. If we divided the seesaw into 1,000 little bits, then there'd be 1,000 weight forces, each acting on a different little bit of the seesaw, each pulling at a different point along the seesaw. That's ridiculous. That you really can't keep track of things that way. That makes the problem extremely difficult. But we do have a trick that makes things simpler, and we call the trick center of gravity. And I'll just abbreviate center of gravity as COG. You can think of center of gravity as the average location of mass. If the mass of the seesaw is evenly distributed throughout the whole 2 meters, then the average location of mass would be right in the middle. If for some reason the right half of the seesaw had more mass and the left half of the seesaw had less mass, then the average location of mass would be somewhere on the right half. In other words, the center of gravity would be somewhere on the right half. But let's say this is a normal seesaw, so the mass is distributed evenly throughout the whole thing. That means the average location of mass is right in the middle. So the center of gravity is right in the middle. That's what center of gravity means, average location of mass. But here's the trick. Instead of thinking of a million little weight forces, each pulling down on a different piece of a different piece of the seesaw, we can think of just one weight force pulling on the center of gravity. And that actually has the same effect as a million little weight forces pulling on a million different little pieces in a million different places. So, in other words, we imagine the whole mass of the thing condensed down to a point, and the point is located at the center of gravity. And then we think of the weight force as just pulling on that one lump of mass that sits at the center of gravity. So that means that if we want to think about the force on the seesaw, the weight force on the seesaw, we can say that it's pulling right there at the center of gravity. And we've imagined the whole mass of the seesaw condensed down to that point, so the weight that's pulling on that point is really just the whole mass of the seesaw times g, acceleration from gravity. All right, those are 2 forces. 2 more forces. There's a downward force from the kid on the left pushing down on the seesaw. There's a downward force from the kid on the right pushing down on the seesaw. Those 2 are normal forces. It's important just to stay clear in your mind about what's going on. Don't call those forces weights, because they aren't weights. That's the weight of the seesaw. And the normal force from the kid on the left, and then normal force from kid on the right. Important thing, when you've got 2 or more forces of the same type, in this case we have 3 different normal forces, you need to do something to distinguish them all, because otherwise you can get mixed up in the algebra. Those are 3 different forces, so unless you want to become hopelessly confused when you start doing the algebra, you must have 3 different names. And an easy way to do that is with some subscripts. Subscript here for, kid on the right. Back, kid on the right, and subscript here. This is the normal force from the kid on the left. Remember, those are normal forces, not weights, but the strength of those normal forces, the magnitude of those normal forces, is just equal to the weight of the kid. Think of it this way. There's 2 forces on the kid, kid's weight and normal force pushing up, but the kid is just sitting still. The kid is in equilibrium, so the net force on the kid must be 0. So the downward force on the kid, weight, and the upward force on the kid, normal, are equally strong. So the upward normal force from the seesaw on the kid, the upward normal force that's supporting the kid is just as strong as the kid's weight. Now, Newton's third law tells us that the upward normal force from the seesaw on the kid has a third law partner, a downward normal force from the kid on the seesaw. That one. And the upward normal force from the seesaw on the kid is the same strength as the downward normal force from the kid on the pushing on the seesaw. That's Newton's third law. But we already knew that the upward normal force on the kid is equal to the kid's weight. So the kid's weight is equal to the upward normal force on the kid. And by Newton's third law, that's equal to the downward normal force from the kid on the seesaw. So in other words, that's equal to the kid's weight. Kid's mass times g. And similarly, this will be equal to the other kid's weight, 20 kilograms times g. All right, now we know what forces are acting, and we know where they are pushing. That's important when we talk about torques, because you can't figure out a torque unless you know how far the force is from your reference point. Well, let's make that our reference point, because if there were rotations, that would be the point around which the seesaw pivots, around which the seesaw rotates. So reference point right there. Now we can write down first an expression that shows how forces combine to give you the net force. Let's do that. We always want a coordinate system in our free body diagrams. That will help us to keep things straight. We know that the net force will just be all the force in the positive direction minus all the force in the negative direction. There's only one force in the positive direction. That's the normal force from the seesaw. And then it's minus all the forces in the negative direction. Minus that force, normal force from the kid on the left, minus that force, normal force from the kid on the right, and then minus the weight of the seesaw. And since we're in equilibrium, the net force has to come out to be zero, because there are no accelerations. That's what equilibrium means. Now, we need an expression for net torque. That is, we need to show how all the torques combine, just as we showed here, how all the forces combine. But to do that, we first have to do one other thing. We have to figure out what those torques are. So let's do that now. Need a little more space here. Okay. There are four forces. Each of those forces could produce a torque. And reminder of the rule. So first, the torque that comes from the normal force from the kid on the left. That's just going to be, first term is the magnitude of the force, which is just this, 20 kilograms times g. And I'll just leave it as 20 times g. I won't do the multiplication yet. Next, times the magnitude of the displacement vector. Remember, the displacement vector always takes you from the reference point or the pivot point, whatever you want to call it, from there to the force. And And so the magnitude of a displacement vector that goes from here to here is just that distance. Well, that's the unknown distance that we're trying to find. That's the unknown distance that I called x a little earlier. So the magnitude of the displacement vector is x meters. That's going to be what we need to figure out. Then sine is the angle between the displacement vector, which points this way, and the force, which points straight down. Right? Displacement vector is horizontal, force is vertical, so there's a 90-degree angle. Sine of 90 degrees and sine of 90 degrees is just plain 1. So this torque is 20 kilograms times g times x meters. Pay attention to positive and negative torques. You have to, otherwise you will get the algebra wrong later on. Is this a positive or a negative torque? Well, as I talked about in previous videos, and then you'll see more of this in some of the assignments, if a torque, basically, the moral of the whole story is, I go into a lot more detail in the videos and in some of the assignments, but the moral of the story is, if a force is able to make a clockwise rotation appear, a clockwise rotation that was not there before, in other words, you're changing the rotational state, that force causes a negative torque, right? Because in this, the way we've set up our definitions of plus and minus, clockwise always refers to a negative rotation. So if it makes a clockwise rotation appear, it's a negative torque, and vice versa. If it makes a counterclockwise rotation appear, it's a positive torque. Well, imagine you're pushing here, and you push hard enough so that things are no longer in equilibrium, but a rotation starts to happen. Well, pushing right here will make a counterclockwise rotation happen. Remember, we're always imagining what would happen if your reference point were an axis of rotation. And if this is strong enough to make rotations happen with this as the axis of rotation, then the seesaw would rotate counterclockwise. So this force causes a positive torque because it makes a positive rotation appear. Counterclockwise is positive. All right. Now we're done with that torque. Next, torque due to the normal force from the support at the pivot. Well, think of this factor. This is the magnitude of the vector that takes you, of the displacement vector that takes you from the pivot point or reference point to the point where the force is applied. But here's the reference point, and this is also the point at which this force is acting. So the distance from the reference point to the point where this force is acting is zero distance. So the displacement vector that takes you from this point to the place where this force is acting is zero displacement. So if we're talking about the torque due to this force, this factor is zero. So the torque is, of course, zero. And then you can say exactly the same thing about the torque due to the weight of the seesaw. For exactly the same reason. The reference point and the point where this force is pulling are the same point. So the displacement between the reference point and the place where the force is pulling is no displacement at all, zero displacement. That factor is zero, so the torque is zero. So those two both give you zero torque. The only other non-zero torque will be caused by this force. Let's see what that's like. The torque due to the normal force from the kid on the right pushing down on the seesaw. Same deal. The first factor is the force, which is the magnitude of this normal force, which in this particular case turns out to be the same as the weight of the kid. 25 kilograms times G. Next factor, D, the magnitude of the displacement vector, which takes you from the reference point or pivot point and takes you to the place where the force is applied. Remember, way back when we started thinking about this, I said this distance was half a meter, so 0.5 meters. And then the third factor is sine of the angle between displacement vector and the place where the force is applied. Well, displacement vector starts here and ends up here. Starts at the reference point, ends at the point where the force is applied. So the displacement vector points straight to the left horizontally. The force is vertical. So the angle between the horizontal displacement vector and the vertical force is a 90-degree angle. So again, you've got sine of 90 degrees, which again is plain old 1. So the magnitude of this torque is just 25G.5, positive or negative. Well, can't ever forget the signs. If this force were pushing strong enough to make the seesaw start to rotate, and remember, you're always imagining what rotations would look like if the rotation axis were right here at the pivot point or reference point, whatever you want to call it. What happens then? Well, you push like this, and the seesaw rotates like that, clockwise. Clockwise rotations are negative rotations, and a torque that causes negative rotations we call a negative torque. Okay, so this plus this, that's just 0, plus this give you the whole net torque, and we know that because this seesaw is in equilibrium, net torque has to be, the grand total net torque has to be 0. So let's just write that algebraic statement. So, net torque is the first torque, which was this, positive 20 kilograms G times X meters, plus the second torque, which was minus 25 kilograms G times half a meter. And that all has to add up to 0. And of course you will get 0 because here's a positive term and a negative term, right? If two things are going to add up to 0, they have to have opposite signs, so everything looks good there. Notice there's a factor of G in both terms there, so I can just divide the whole equation by G, and that simplifies all the rest of my algebra. That's why I did not multiply mass times G earlier. So divide the whole equation by G, and now all we have left on the left-hand side is 20 kilograms times X meters minus 25 kilograms times half a meter equals 0. You do a little bit of algebra and you rewrite that as 20 kilograms X equals 25 kilograms 0.5 meters. Solve for x by dividing both sides by 20 kilograms. So 20 kilograms divided by 20 kilograms, that's just 0.1. So all we have is x on the left-hand side. 25 over 20, we can write that as 5/4. Simplify that a little bit. Times 0.05 meters. So when you take 1/2 and multiply it by 5/4, what you'll finally get in the end is 0.625 meters. So in other words, what's happening here the kid on the right is the larger kid is 1/2 meter away, and as everyone who's ever been on a seesaw knows, if you want to balance, the smaller kid has to be farther away, and that's the result that we get here. The smaller kid is farther away. 0.625 meters away, or 12.5 centimeters farther away from the center than the big kid is. So that's one example of equilibrium and thinking about torques. Go to part 2 of these videos and I'll show you another example.